Thank you. So before I start and tell you a little bit about myself and what we do, I just want to get a bit of a measure of the room. Who here works in machine learning actively? Okay, great. Who here until today or before has absolutely had very little exposure to machine learning or deep learning? Okay, so, and who here is a business person? It's not a bad thing. I hope so, otherwise I'm out of a job, so. No, but just to get a little bit of a feel of the audience. So let me tell you a little bit about myself. So let me start by telling you just a little bit about myself so you know how serious to take me today, essentially. So I'm one of the co-founders of Sourced, and at Sourced what I'll be talking about today is a lot of the technical stack and some of the kind of interesting things related to building a massive data pipeline on top of code. So I'm a huge computer geek, as Alexei already presented me, although I'm a huge computer geek who's had absolutely no formal education. I've been programming for most of my life. I've been working with neural networks for quite a few years. Huge passion for programming, huge obsession with neural networks. But I'm actually not a formally trained expert in programming languages or a formally trained PhD in mathematics or machine learning. I feel very privileged and lucky though because I get to work with about 30 people, most of which who are actually formally trained PhDs or programming language researchers or hardcore compiler guys or engineers. So I feel very privileged to be able to do so. So I'm going to talk a little bit about one of the core fundamental things we believe at Sourced, and I'll later come back a little bit about how our manifesto, some of the things we believe, actually play a very large role in how we treat data and how we build a data pipeline. So essentially it comes from one very fundamental belief that we have, and it is not a very controversial one, is that we consider programmers closer to artists or writers than we do to civil engineers. Essentially saying that if I'm a developer, my raw material is programming languages. If I'm a writer, my raw material is the English language in the dictionary, and if I'm a painter, it's my palette of colors. And based on this raw material, it's up to my own ability and creativity to create something. Right? I can write a book, or I can be Glenn Greenwald writing for the Washington Post, or I can be a developer creating a web app or working on neural networks, or et cetera, et cetera. Right? At the end, it's up to our own creativity and ability to create something. Why does this matter so much in relation to what we do? So if we look at technology, pretty much since the beginning, the last 30, 40 years, it's continuously grown in orders of complexity and magnitude. This is one of the things that almost all of us can agree on. But what's really surprising is that we've written these trillions and trillions of lines of source code, but we're actually not leveraging them. Right? We've written already trillions of lines of code, but we're not using it to improve the way we program, improve the way we build software. We're not learning from code that's already written. Right? And when you're not learning from a huge, beautiful data set, there's for sure out there some geeks like myself who get very excited about it. So at Sourced, we believe that AI on code is a field that matters, is that we can learn from all the source code that already has been written. And I saw earlier the question from Michael, what's the difference between AI and ML? It's purely who you're presenting to. At the end of the day, they're exactly the same thing in my opinion. So you can replace AI with ML. But what I'll be talking about a little bit today is our quest towards how do we turn source code into a data set that is as important as computer vision is today or natural language is starting to become. Right, if we go a little bit back through the history, particularly of deep learning, since kind of the inflection point in 2012, since it became popularized again, right, since we came out of this AI winter. If we go back, we essentially saw in 2010 ImageNet being created. Right? ImageNet is probably one of the most quintessential data sets if today you work with things like convolutional neural networks, or particularly in computer vision. And ImageNet was a data set created by Dr. Fei-Fei Li while she was at while she was at Princeton. To essentially combine this huge data set called WordNet that we had, of words that had semantic similarity to each other, with 100 images each. She said for every single word group, we want to have 100 images that actually are label. The text is a label on top of these images. once we created this data set in 2010, the whole computer vision field all of a sudden had a very, very large, beautifully labeled data set that they could work with. In about 2012, a few guys who had been working in neural networks started actually applying some of the techniques that they had seen over the years not work to this data set, together with the fact of the breakthrough starting to use GPUs for computations of gradients, right? Essentially the main thing that we use in neural networks. So since then, about 5 years later, we're back in a full-on AI hype. We're starting to see it in every single field and every single data set that we can imagine is being applied to it. But how I look at it, you have essentially images today, you have speech, right? Audio, voice, music, and you end up having natural language. And probably in that order is also from ease to difficulty. We're getting really, really good at understanding things in computer vision. We're getting a lot better than we were in understanding things in audio, and we still really, really suck at understanding things in natural language. But code is kind of this data set that falls a little bit in between any of these things, right? Code is not natural language, code is not an image, code is not a music. It's essentially a very, very well-defined semantics that we use to instruct our machines. And the only reason we have programming languages is because we don't want to deal with ones and zeros. Right? One of my favorite things to do is to go back through these interviews with some of the kind of like legends in our industry, like Donald Knuth or Simon Peyton-Jones, like the early programmers who made a big impact. And you'll all hear like, when I started, I was dealing with punch cards, right? And at the end of the day, we have just created these languages to make it easier for ourselves to deal with state changes. So why is it interesting to start applying machine learning and particularly deep neural networks on top of code? So there are several areas in terms of computer science, and there's many more that we personally find interesting. The first is what they call in academia inductive programming, or also part of the field called automatic programming, which essentially means if I have a sample of inputs and a sample of expected outputs, right? I have the numbers 1, 2, 3, 4, and I have the expected outputs 8, 9, 10, 11. What is actually the piece of code that transforms these inputs to these outputs? That's pretty much at its core what people talk about inductive programming. When you hear this, you already start seeing this is a machine learning problem at the end of the day, right? It's a transformation of data from one form to the other. I'll talk a little bit later about how in particularly this is an interesting area and what you can do with it. But very practically, developers, we write millions and millions of unit tests, right? Unit tests are essentially what we write to be able to see if our code has the expected behavior that we want. Right? And in a unit test, you'll say, okay, for this function, I'm going to pass it these values, and I expect this output to be able to happen. So all of a sudden, if you start thinking, we have a data set already of expected inputs and outputs, and the code that is supposed to make it happen, and an ability to check if it actually does. Right? Then we talk about transpilation. Transpilation is essentially the field in computer science of going from one programming language to another. Right? And if you look over the last 30, 40 years, particularly with our developers' kind of ability to consistently want to jump from one hype onto another, right? Consistently changing programming languages, sometimes for the better and sometimes just because it's trending, or sometimes because Google is putting a lot of money behind it or another company is. Can we actually have systems that are learning how to convert one language to another instead of massive rule-based systems? Dynamic memory allocation. So today, a big part of programming has to do with dealing with memory. In higher level languages, it's more abstracted. You might not ever realize it if you're in an interpreted language like Python, unless you're a data scientist and you run out of memory. You start realizing it very, very quickly. But in many cases, it's more and more abstracted, right? But what's interesting, we recently did some work where we took video games and we started training on the video game data while people were actually playing and using it to see if we could predict what memory we needed to allocate at compiler level ahead of time, and could we predict it more accurately than what the compiler itself was actually doing rule-based. Turns out we got about 98% accuracy. This work we'll be presenting in the coming few months to be able to predict memory. That is not that interesting today if you're working on my Dell computer, because at the end of the day, training that neural network and inferring from that model will require more memory than it saves. But Apple just announced the Core ML framework to start using the GPU for machine learning on their phones. Samsung is starting to include neural chips into their phones. And all of a sudden, we can start getting really, really good at not just predicting memory, but also predicting what the user is about to do next, and actually start loading values and state beforehand. right? So all of a sudden with machine learning, it doesn't just touch the code itself, it also starts touching the way our devices are. Code similarity, right? How in many, many cases as developers we're applying patterns that have been applied thousands, hundreds of thousands of times. That can be simple patterns like I'm using an API or a library that is very popular. That can be stylistic patterns in terms of how we do something. That can be a little pattern in terms of where I put an if error nil statement if it's talking about Golang. And so in the end, understanding similarity between code on both a semantic level, a syntax level, and a style level can be incredibly useful for things like code search or recommendations. Style transfer. So there's been this field in computer vision. You might have seen like articles online or nice little tweets on Twitter where you take a painting and you take a photo and you transfer the style from one onto another, right? And it looks amazing. It's actually one of the areas I would say in terms of kind of creative AI that has worked the best and is having great results. But in code, there's also style. Actually, if you ask any single developer to review someone else's code, you'll very, very quickly realize there's style in there because we're highly opinionated people who will start saying, oh, I don't like this or I do like that. And the reality is a lot of this I like this or I like that has absolutely nothing to do with rational reasons, right? There are some objective arguments to be made in some cases, but I don't know, I prefer using pattern matching for recursion. Hence, I'm wearing this t-shirt. For those of you who like Haskell or know about it. But there's lots of other ways I can do recursion inside Haskell. Why do I do one or the other? Just because. It feels nice to me. I like the syntax. I like how it aligns, right? Or even the fact that there's a lot of developers who are opinionated about languages because of their syntax, not because of what actually is below the hood. Can we actually have style automatically transfer? Where is this very applicable in the world is you come into Google, you come into Facebook, or any large code base, IBM, and you'll start having tens of thousands of developers who all have their personal opinions and who all have their personal style, all working on the same code base. Right? What if you could actually normalize that style? Or what if I could extract the project, view it in the style I want to view it, but commit it into the style of the company? Right? So there's interesting areas you can do here. Neural compilers. Earlier, the talk before, you heard a lot about labeled data. Most of the work we do is in unsupervised learning. But actually, if you think about labeled data and you think about transpilation, I mentioned earlier programming languages at the end of the day where they're just abstractions on tops of ones and zeros. And probably the lowest abstraction that we as developers like to work with, or if we have to, is assembler. Essentially, this kind of small machine language. It's a machine language that essentially is a control flow and it doesn't have all the crazy branching structure that you have in more higher level programming languages. So when we write a compiler, right, something that turns a high-level programming language into instructions for the machine, we are essentially, again, having a data set of two sides. We have the programming language and we have the machine language. And today we have these compilers that are written of thousands and tens of thousands of rules that are highly optimized. There's even companies that pay to have custom compilers based on their use cases in the company. But what if actually a compiler wouldn't have to be based on rules, but could actually learn and change over time? Right? Neural compilers, vulnerability detection, security detection. There's a lot of areas. But the reality is today, in every single one of these areas, there's nothing running in production at any given company in the world or in any given tool that is really applying machine learning on top of source code. When we started about 2 years ago, this field was completely new. We actually started putting the words AI on code together. And now we're starting to see startups and research happening at Microsoft and Google. And we're starting to see more and more people thinking about this field. And almost everyone can agree that in the next few years, no one knows if that's 2, 5, or 10, AI will influence the way we program and the way we build software. But the reality is there's nothing out there today to make that happen. And that's essentially what we try to do at Source. Can we create an open source stack that allows every single person in this field to be able to get started quickly and start building these things? So, mention data, right? So where are we gathering our data from? At Source, we have a pipeline that gathers every single public Git project in the world online. Doesn't matter if it's a self-hosted cgit kernel, if it's on GitHub, which is by far one of the largest data sources, if it's on GitHub's Chinese equivalent, if it is on any given site personally hosted. We have crazy architecture I'll talk a little bit about later. And when we started, just on the GitHub data set, which is by far like 80% plus of the code, there are a little over 3 million developers who had publicly committed code online. Today, a little over 2 years later, that's 10 million people. right? So we're starting to see that this growth of code that is publicly available keeps on growing exponentially. And a lot of that is credit due to sites like GitHub, which are starting to push forward, this kind of collaborative, social way of coding. A lot of this code that's out there from developers is not classic open source that you know, right? The perfectly licensed projects that are in use cases in many different places, but it's in many cases also millions and millions of projects of developers who just decided to play with something or put something out there for themselves. So why now, right? Why are we interested in AI on code today and have been for the last 2 years? This is our thesis, and I think in this room it won't shock many people. The number of developers is growing exponentially. Besides data that you can look at in the world, the easiest way to look at it is to call up all of your friends who have young kids who aren't programmers or who don't work in tech. And you start asking them like, do you want your kids to learn programming? Are they learning something in school? And you'll start seeing that all of a sudden, in most cases, at least in the people I know and the people I've asked about this, their little kids who are 3, 4 years old are in some way being pushed into being a developer. Right? And if you go to India, you go to China, these are countries where you see this far more. Right? For me, the shocking number is 600,000 people graduate each year in computer science in China. Only 60,000 in the United States. Right? We're screwed here at the end of the day. No offense. But so this is one of the things, right? This number is growing exponentially. There's 21 million software developers we have in the world today. I personally believe within the next 10 years that will grow an order of magnitude. Software is eating the world, right? That's the phrase that essentially classifies California, or at least the Bay Area. Programming becoming a new lingua franca. And one of the nice things that you see around this is how you look at how people program in different countries. Right? Most variables, most comments, everything is in English. But code for itself can speak, even if you don't speak the same language. Complexity of code is increasing, right? We don't just see this in our own code bases. We also start seeing this in consistent failures. Right? British Airways in the last 12 months, their entire system went down twice, right? And so is this because of hackers, or is this because of, they claim wasn't because of hacking, claim because of issues in their code? But at the end of the day, these systems are becoming so complex that both the security aspect and the actually maintainability aspect and the points of failure are just becoming too many. And this is a massive industry at the end of the day. Data sets are becoming enormous, right? In our case, source code. We have a data pipeline that goes into petabytes of source code. Right? So close to 2 petabytes of source code written. That's a data set that is hard to find today and anywhere. Right? Computer vision data sets are in the petabyte, but we're talking here about text. Right? GPU computing. At the end of the day, I think we can all be incredibly happy, at least for us who are working in the field of neural networks, of the rise of computational power with GPUs and the decrease in cost at the same time. Right? And then neural networks are cool again. Right? Since 2012, they're cool again. And we hope that they'll stay cool for a little while. But what is most interesting to me is how many people have been attracted to this field. Right? If you look at one of the largest conferences, at least academic conferences in this field, is called NIPS. If you look at NIPS in 2012, I reckon it had about 300, 400 paper submissions. This year it was over 5,000 papers submitted. Right? So it gives you a little bit of an idea of like what's happening here, and it's becoming pretty obvious. So Alexei today asked me to talk a little bit about our pipeline. So since we're not a hardcore technical audience from what I've seen, I will go through some of the things we do, and if somebody says, hey, I want to go deeper into that, you can either ask me right here on the spot or we can talk about after. One thing that makes us a little bit different than probably most of the companies you'll find here in the Bay Area is that we're not a big fan of doing things on the cloud. When you're dealing with petabytes of data, and you're trying to go to Google Cloud, or you're trying to go to Amazon, your storage cost for the high input-output, right? The fact that you need to read and write your data quite a lot, in our case, primarily fast reading of our data, means that you're getting to a bill of several $100,000 a month pretty quickly, right? When you're a startup, we're lucky, we're a little bit larger than just out of the box startup, but that becomes pretty darn expensive, right? So one of the things that we decided pretty early on was to go bare metal. So we've actually been working with a hosting company, in this case in Paris, one of the largest in Europe, where we built essentially 60 high-spec CPU workers that cover about 2 petabytes of storage, close to 12 terabytes of RAM, and thousands of cores. So it gives you a little bit of an idea of like trying to do this on the cloud. The equivalence is about $15,000 a month versus about $250,000 a month. Yeah, it's a very large difference. However, and there's one very, very big if, our DevOps team and most of our engineering team, it's partially remote, but is based in Madrid, Spain. Right? So we have a 3-person infrastructure team, and a good 3-person infrastructure team here in the Bay Area will run you easily about $500,000 a year. In our case, we have that significantly less, just happens to be because of the cost, the market rates for salaries back in Spain where our main office is. So you always have to take both things into account, and the fact, of course, you have a lot more points of failure. However, for us, our data pipeline is not one that is exposed to the outside world. It's not one that has millions of users banging it all the time. We don't have load balancing issues, right? It's purely for ourselves. And in that case, having bare metal makes a huge difference. Then pretty early on, we tried lots and lots of different things with all those GPUs that we need for training. Right? So we started with a box in the office, then we spent a ton of money on Google Cloud. But if you're doing cutting-edge GPU computing, in almost all cases, you want to be working on the latest architecture that comes out in NVIDIA. For us, the difference between a Kepler and Pascal architecture and chips is about 2x cost and speed savings. Right? So what happens in this case, NVIDIA does something very, very smart that isn't very publicly discussed. And does anyone here work for NVIDIA? No? Okay. Is that they have the line of chips that they sell into the deep learning world. The P100s, and they have their boxes, the DGX1s, kind of the Rolls Royces of deep learning. They have all of these chips out there. But when you look at bang for a buck processing power, what you want is the chips the gamers have. You actually want the 1080 Ti, you want the Titan X, you want these cards that are, in many cases, 3 times cheaper for what you can actually get for processing and energy usage. But NVIDIA does something very, very smart. They said, look, we're licensing-wise, cloud host computers or cloud hosting companies aren't allowed to actually rent these out. So Google Cloud, Amazon, they're not allowed to actually buy these chips and put them in their machines. Some interesting things are happening in this industry that I don't know enough about, because now NVIDIA has actually their own kind of cloud that they're starting to set up, and it looks like they will allow it. But at the time when we were doing so, we couldn't get access to these chips. And at the same time, because Google and Amazon, they have quite a shortage in many cases of supplying the latest architectures and getting them actually from NVIDIA, it means that you're almost all cases working for about 9 to 12 months on an outdated architecture. Right? So now the Volta has come out, and actually Google has just announced about 3 weeks ago that the Pascal chips are now there, right? About a year later or so. So if you are very reliant on the latest speed improvements, the latest architecture changes, in our case that's to do with some floating point math operations, it's just something to keep in mind. So what we started doing now, actually, it's happening while I'm here, we started actually building our own little mini data center at the office. We realized that in the end, for us, what made a lot of sense is we actually just build part of our office into a data center. We start taking servers that fit exactly the same specs as we can keep them with our hosting providers. We put them in the office, and over time we keep on moving them out to the data center. Right? Literally take the box, ship it, and put it somewhere else. When you start dealing with these data pipelines where you're doing a lot of GPU processing on a lot of data, you hit into very stupid practical constraints. One of the biggest practical constraints you get is energy consumption. For most data centers that you'll find, a rack is allowed to consume about 3 kilowatts of energy. So any hosting company that's out there prefers to stuff that rack with 15, 20 CPU machines that don't have GPUs in them, because an average machine with GPU will take about 400, 500, 600 kilowatts. Right? So you can't put as many machines in the same physical space. Right? So there's a lot of these silly constraints that you get to when you start dealing with at least processing at scale. And you got to start making your own decisions of what makes sense for you. The only thing I can say is that it's not that necessarily bare metal is better than the cloud, or being crazy enough to put things in your office is the right decision, or co-located hosting, or these things. But at least spend some time figuring it out what makes sense for your use case. Right? In our case, we have this essentially processing cluster that can prepare with Spark all of our data sets. By the time it goes in of petabytes of data, the data set that will come out that goes actually in deep learning is usually in the terabytes or in the hundreds of gigabytes, which is relatively easy for us to transfer. And then actually transferring that data set, in our case, literally to our office, makes most sense. Right? But this is very specific for your use case. We are big fans of containers. Probably every single developer is these days. It's a bit of a hype, but in our case, it makes a lot of sense with the way we actually manage our architecture, right? The fact that we will still sometimes go to Google Cloud if we need to process something in time for something, that we will switch between our bare metal processing and the actual kind of mini server rack back at the office. It makes a lot of sense to be able to have a format that you can easily move things around with. Also, at the same time, there is an interesting trend happening, or starting, actually it's not happening yet, because I know maybe of 2 or 3 companies that are doing so, but a lot of the people in the container industry are talking about this, is instead of moving your data from worker to worker, why don't I move my container images from worker to worker? So actually keep the data on the machine and actually start moving the containers instead. So you can build processing pipelines where you essentially keep state of what's happened in the container without moving the data. Right? If you're dealing with very large amounts of data, this can actually save you a lot on the I/O operations, the networking operations that you have in between. Anyways, if someone's interested in this stuff, we can talk more. I'm not a hardcore DevOps guy, but I feel like I know enough to talk a little bit about it. And then I won't go into the basics too much today, but we run pretty much plain vanilla Spark pipeline. It's not the best Spark, it's not the greatest, but it works. It works very well. Most of the tools, and I'll talk about the things that we build as binaries and we run on top of that. And then we use TensorFlow. We use TensorFlow not because it is the best library, not because it's the most performant library. We use it because there's about 4x more developers who use it than the next best library, right? TensorFlow has essentially won in terms of size of community. And when you're looking in terms of particularly the work that we do in deep learning, what you want is you want the things from the latest research papers as quickly as possible to end up in code. And then from code, you quickly want to end it up in actually distributed way of doing it, and then a distributed performant way of doing it, right? And so often you're working in a vacuum, you're working on top of your own stuff, but a lot of the architectures that are coming out from other researchers, from other groups, from other companies. In most cases, we see that those implementations hit TensorFlow first, and we can actually go work on them and improve them. So we spent a lot of work together with Google actually improving some of their models in the TensorFlow models repos. So you can actually see as a company, we dedicate a lot of time doing tons of pull requests in the official TensorFlow repos, both on the core and on the models, because we see, hey, look, if it's coming out in a research paper, we can put it there, and together with the community, we can build it. And so this is why we've done so. It's actually, I think, the reason a lot of people are going for it. There are some extra benefits in TensorFlow as well, but the reality is, for many specific tasks, there are other frameworks that perform a lot better, at least in my opinion, for now. Right? You kind of have to think, where do I bet on? And I personally prefer to bet on the 2,000 deep learning researchers that Google is hiring right now, and the other 27,000 engineers that they have. So I won't go too technical into a pipeline, but when we look at a pipeline, we look at it both from an actual, how is our organization structured, how is our data structured, and how is it actually technically structured. So for us, our raw material is always code. And code starts with data retrieval. Where do we actually get all these projects and code from? So we have a data retrieval team in Source. It's about a 7-person hardcore engineering team with guys who, actually it's a very, very team. The lead on that team won several times the AI vandalism competition for Wikipedia, has worked on crazy large data pipelines, in-memory query engines, and the most junior person on that team actually worked with Dennis Ritchie on Plan 9. So that gives you a little bit of an idea in terms of the different type of people. Then we have the language analysis tools, and I'll talk a little bit about that later, but it's essentially how do you take code and turn it into a format that you can actually work with it. Then we have the machine learning team, which in our case is a little specific. So one of the things that early on we realized, since we're a relatively small company, about 30 people, we didn't have the ability to go and take the top researchers from DeepMind or the top guys from Google Brain. And so we decided something different. We said, let's find the people in the world, hence we had the code of 9 million developers, so we could look at the code. So let's find the people in the world who follow essentially this kind of profile. They need to have a hardcore math or physics background. Right? At the end of the day, if you're doing things in deep neural networks, you can go very, very far with getting the stuff working, but if you don't have a strong math foundation, you're gonna hit a roadblock at some point. So let's find people who have that strong background, who then after, for whatever happened in their lives, actually decided to go from math to physics to computer science and became really hardcore computer scientists. In many cases, compiler guys or people who were really like doing low-level programming. And then around the year 2012 also woke up to this hype and moved to machine learning, and particularly deep neural nets. So in our case, that turned out actually, based on our data set and a few coincidental occurrences, that we found everyone who really fits that profile to be based out of Russia. And so, and that had to do with the fact, actually later speaking with people, I was just giving a talk in Moscow last weekend, the weekend before last, about this. And I was talking to a lot of guys, and I was like, look, why do you think this is, right? And they said, well, in many cases, you know, we studied math or physics, and we couldn't find interesting jobs that we wanted to go into. And, you know, my dad was doing something with computers, or I came across this book, and I got excited about computer science. And that actually ended up going into Olympiad programming, Olympiad math, Olympiad programming. And from there, I ended up later on in machine learning. So we made a pretty conscious decision as a company early on to focus a lot of our efforts in terms of recruiting and attracting talent pretty much specifically on Moscow, St. Petersburg, Tomsk, and a few other cities inside Russia, where we found people who really had this background and also in many cases fitted our culture. And today, funny enough, I would say close to 1/3 of our team is actually Russian. We're from 9 different countries from all over the world. I'm Dutch originally. We're based out of Spain. My co-founder is German. So we have people from many different places. But turns out that made a lot of sense for us and allowed us to hire people that didn't actually want to come, in many cases, here, or had offers from Google or Facebook, but said, hey, it's too far from family. I want to stay in Europe. I don't want to go that far. And actually allowed us to find really great people who are on our team. And then data sets, right? At the end of the day, a pipeline along different steps that could be on a data retrieval, that could be on language analysis or machine learning. At the end, you spit out data sets. And I'll talk a little bit later about models and demos. So just to give you a little bit of an idea of some of the things that we have in our data pipeline. And I'm going to keep it very simple. We start with needing to discover where there's code. Essentially discovering where there's Git projects in the world. Right, so we have Rovers. Rovers is a project that's, Rovers and Borges are actually being open source next week. Everything else that you'll see is fully open source. But these are essentially crawlers and API connections to start building a massive queue of lists of every single Git repo in the world. So that we end up with this massive list of Git URLs. And with Borges, we start Git cloning and storing every single source code project that is out there. And we don't just do this once, we do this continuously. Right? Essentially, every few days, that's the maximum time a project's allowed to be outdated. We keep on Git cloning again and gathering this data. What's interesting about version-controlled data, at least in particularly of source code, is when you do all of this, you get about 100 terabytes of code. It's a lot. It's not that much. But then when you actually start diffing commits, right, going back through the history of version control, you end up with more than 10x more data. Right? You start ending up in the petabytes range of data. And this is very interesting. I think the same thing probably would apply to documents and other things. But if something is version controlled, you can probably discover a pattern like this. For us, what was interesting is that along the way, we needed to build a lot of stuff that hadn't been built yet or hadn't been built in a way that was usable to us. We needed to actually modify the implementation of Git. So today we have the world's most popular implementation of Git. It's being used by tons of different companies and all over the world. And we actually built Git from scratch. It's a little crazy. We needed to realize that the way we were storing data, the way we were archiving format, we needed to be able to have a seekable index. So we needed to be able to take a piece of data, compress it, have an index, compress it, have another index, compress it, and be able to go through those indexes. Right? Because once you're dealing with this much data and you're on a budget, right, you don't want to go and spend hundreds of thousands of dollars in the cloud, you needed to be able to compress it and effectively manage it. Turns out that we actually needed to create our own archive format. Tar and the others didn't do this. So you find yourself very often, even though your whole focus is on AI and on deep neural nets, you find yourself with a big part of our team, in our case almost 70% of our entire team, focused on actually the data pipeline itself, not on the fancy models or on the fancy architectures. So let me just be aware of time. Yeah, I think we're good. So code is not the same as language. It's not actually this linear sequence of tokens, right? When we look at writing or we look at code, we essentially see, okay, it's one token after another. But in the end, when the compiler gets code, right before it starts turning it into a machine language, it gets an abstract syntax tree. Essentially, it's a tree structure of code. Right? If I have an if statement, I will have the two conditions as nodes below and the values to those conditions below that. And at the end, it's essentially a tree. And one thing that holds true in almost all, actually pretty much in everything in machine learning, is how you represent your data next to the integrity of your data is crucial. Right? Sometimes you can represent your data just as text, in our case. Representing it as a tree makes a huge difference. One thing that's interesting for those of you who really want to experiment and do some crazy things, sometimes taking your data and representing it in a format that you don't expect is natural to it will work better. Like I've seen people be able to take things like text and try to represent it as sound waves, and for their problem, that allowed them to actually get much better results. Right? And I've seen, so there's a lot of interesting things you can sometimes do with transforming your data into different data structures. In our case, it makes a lot of sense that code is an abstract syntax tree. So I won't go too much into this, but essentially we built an architecture that has a server, and I send a file to the server. Any piece of code, could be, I don't know, crypto.py. It will detect its language. It uses a machine learning based approach to detect about 400 languages, nothing too crazy or fancy. And it will find a container and in that container is a language driver, a native AST parser, and something called a normalizer that annotates it and turns it into a universal standard. For those of you who are programming language freaks like me or researchers, we're taking every single programming language in the world and turning it into a universal abstract syntax tree, an actual representation for that. This is a massive undergoing project, started about 4 months ago. We're getting a lot of people involved. And at the same time, it needs to perform incredibly fast. Right? Trying to take code and parse it into this tree structure is not an easy task. So I'll talk a little bit about some things a little bit more general. You see here 3 libraries, and all 3 of these libraries were created from us by scratch, not to solve new problems. Actually, all of them are classic computer science problems, but to solve them for the first time in a performant manner on GPUs open source. I'm absolutely certain that we've replicated the work that for sure is inside Google, inside Amazon, but in all cases is closed sourced, and we haven't seen in the public domain. So I'll start at the bottom. One of the most probably early things you end up doing in machine learning is clustering, right? K-means clustering, k-nearest neighbor search, right? This is one of the things where I have a data set and I say, okay, based on several features, cluster it into 10 clusters or 20 clusters. When you're dealing with code, you, in our cases, in many cases, have per project tens of thousands of features. We use language embeddings. I'll talk a little bit about that later. And we have not 1,000 documents or 1 million documents. We end up with billions of documents. So how do I take this very high dimensionality vectors, a vector of 512 dimensions, I have a bag of hundreds of millions of it, and actually cluster them based on their distance or similarity to each other? Well, I can tell you exactly how much that costs on Google Cloud. It costs about $50,000 to try to do that with a bag of 16 million documents, and for every single document have a vector of 512 dimensions. That's not feasible. And pretty much the moment we saw that cost after we ran it, because we needed to run it, we said, okay, what can we do that actually avoids that? And what we saw, there's a lot of low-hanging fruit today in actually writing direct implementations on GPUs. Right? I'm essentially advertising NVIDIA here, because we write a CUDA library that is highly optimized to do k-means clustering and k-nearest neighbor search on top of GPUs. And now I can take 2 Titan X cards or 2 GTX 1080 Ti's that will cost me $1,200 to put into a machine. And I can run that entire $50,000 experiment in the course of about 15 minutes on these 2 GPUs. Right? So when you're dealing with these kind of problems, which essentially at the end of the day are matrix multiplications, then you should really consider, what if we write something that works on a GPU? If you are, please open source it, because nobody is open sourcing their stuff that's on GPUs in many cases, so it will help a lot of people. This, until 2 weeks ago or 3 weeks ago, was by far the world's fastest implementation, hundreds of times faster. We just got beat by Facebook. We were a little bit upset. We're like, wait, we're not that bad. Like, how did they beat us? Turns out the guy who originally invented Kmeans and all of the implementations for the last 15 years have been working on optimizing it and actually beat us. It's called FAISS. The only thing is it's a research-only license. So if you're dealing in commercial environments, we're still actually the fastest. And for some use cases, we are as well. But essentially, kudos to them. In many cases, when you're dealing with very, very large data sets and you're trying to do fancy stuff with neural networks, you are finding yourself in a position where you need to start reducing your data set into something manageable. Right? I have 1 billion documents, but I want to start checking them pairwise to each other based on some features. That's not possible. Right? It's 1 billion times 1 billion. It's essentially an NP-hard problem. So one of the old school techniques that still works really, really well, and many people try to do lots more fancier stuff today, is just hashing. Right? Just using hashes. And there's particularly a technique called weighted min hashing, which essentially creates a hash of a document or of any piece of content that you have, and allows you to start comparing the similarity of that hash based on something called Jacquard similarity. Essentially, I can say, give me this huge set of documents, create a hash for every single one of them, and now show me all the documents that are 70% or 80% similar in terms of their content. So weighted min hashing, again, this was a problem that on CPUs would cost us tens and tens of thousands of dollars to be able to do, comparing software projects if they were forks of each other, but actually not marked as forks. So what we decided to do is say, what happens if we actually create an implementation on GPUs? Pretty much the same thing as I mentioned earlier. Takes about 15-20 minutes to train on top of 2 or 3 GPUs, and will run instantly after with inference, versus actually doing it on CPUs and spending tens and tens of thousands of dollars on the cloud. So there's a lot of problems where GPUs don't make sense. But if you're doing floating point math, if you're doing matrix multiplications, anything essentially at the end of the day with numbers, to put it very bluntly, have a look at if it makes sense to write libraries directly on GPUs. And then we have something called WDRelax. WDRelax doesn't have a very sexy name, but it's, in my opinion, one of the most applicable libraries for almost any given problem that you face today with any type of text content, no matter if that's code or if that's natural language. So earlier, I only got to see part of Michael's talk, but as far as I understood from his talk is that they have a massive amount of documents, and they want to be able to understand the similarity between those documents, right? In many cases, or make recommendations. So what WDRelax does actually out of the box is it says, for every single one of these documents, whatever you want to use, try to create some embeddings for the words in them. So there's a lot of interesting work that's become very, very highly popularized over the last few years called word vectors, or word2vec, or word embeddings. And essentially what that is, it's a model that has learned the co-occurrence of words. If I have a given word, horse, how does it co-occur with the word stable, right? If horse and stable are most likely close to each other in its vector distance, in its Euclidean distance, or whatever distance measure you take, horse will be closer to stable than horse will probably be to computer. Right? And these word embeddings have turned out to be unreasonably effective in many, many use cases. It works very, very well to be able to understand semantic similarity and context. In our case, we do some crazy stuff on top of natural language in code. I mentioned earlier, yes, programming languages are very small. They'll have like 80 reserved keywords, and with those 80 keywords and sets of tokens, you can program anything you want. But then as developers, we name things all the time throughout our code. We name our variables, we name our functions, our classes, and essentially what you end up with when you analyze 60 million projects like we do, you end up with 2 magnitudes more vocab than you have in the English language. You end up with 20 million tokens that are actually unique. So what we decided to do is that we want to understand natural language in source code, and the ability to understand natural language in source code is to actually extract everything that we've named ourselves and try to find a similar type of embedding for that. So when we have a project, we will take all of the unique names out of that project, all the names that are essentially that developers have named or have used from other libraries. And for every single name, we'll look up the word vector. We'll look up the embedding that we've trained on another model. And all of a sudden, we have this bag of embeddings. Essentially, it's thousands and thousands and thousands of vectors. We have a bag of thousands of vectors, and I want to compare it against 60 million other bags of thousands of vectors. right? And those 60 million other bags of vectors in our case are representations we have on code, but that can be things you extract from natural language. It doesn't even have to be natural language embeddings. In most cases, when you're dealing with things in machine learning or data science, you have some form of vector representation, and you'd love to know the distance. So WDRelax is an implementation of the word mover distance problem in computer science, which has proven really, really effective to be able to actually start taking this bag and seeing which are the bags that are most similar. So what that allows us to do in very fun cases is I can take the vector for the word beer, and I say compare it against 60 million projects. And I will find all the projects that are highly related to beer. Or I can take, earlier I mentioned we have an implementation of Git. I take the bags of vectors for the project Go Git, and I will find all the projects that are actually trying to do the same thing as Go Git. Right? And this can apply on documents, this can apply on text, it can apply on other things. So right now, all of the links you see in my slide are essentially individual projects. One of the things we're working on in the next, actually this month, and hopefully done by the end of the month, is a fully new site with documentation, examples, that it makes it easy for every single person who wants to get involved in terms of applying neural networks or any type of machine learning on top of source code to be able to start using these things out of the box. So I'll just talk today quickly about, I talked earlier about word embeddings. This is something just to write down. If you're expecting that you want to do something on top of text, you want to have some form of embeddings for words, and you've heard about word2vec, and you've heard about these fancy things, and you're dealing with a lot of documents, go to Swivel. Swivel is a model created by Google. It was a paper released about a year and a half ago by Chris Watterson, and it's essentially a distributed way to compute word embeddings that is insanely fast and scales with the number of vocabulary and not with the number of documents. This is pretty much the only way today you can create word embeddings on top of very, very large corpuses of data. So it just makes sense to know, and I'll show you a little example of a small scale one that's fun. So every single dot you see here, and there's about 10,000 dots because after 10,000 my browser blows up, is a name of a function in the Linux kernel. Right? Linux kernel is probably, or is one of the largest software projects that is open source in the world. And what I've done is they are, in this case, embedded in 100 dimensions. That means every single one of these functions has essentially a 100-row long vector. In our production stuff, we use a lot more. And I've essentially decided to represent it in 3D with a technique called TSNE. TSNE is a really nice technique to visualize high dimensionality data in 2D or 3D. And in my opinion, it's by far the best technique today. What is interesting about this is let's start looking up, and I will also take suggestions from the audience, but I mentioned earlier cryptography. And let's see, what's happening with my mouse? And here I see when we go towards crypto, I see a little cluster. Let's get it back there. I don't know how well you can see this, but what you start seeing is that all the functions that are in this case understood to be semantically similar near crypto are DES, cipher, CHCR, keys, authentication, encryption. And once I go in this, I always like finding the random number generators, which are here somewhere. Let's have a look. Here, RNG and PRNG, which is right on top of it, the random number generators, all the functions that actually share semantic similarity in terms of cryptography. Right? You can imagine not just doing this on code, you can do this in natural language, you can do this on any corpus of text data. For code, it works very, very effectively to start understanding what actually is similar. What is also interesting, if anybody here is a developer wants to give me a name of a function they think is in the Linux kernel? No? Seek? Seek. Okay, let's look at seek. I see seek here. So let's find it. Okay, so this is interesting. I've never looked up seek, but you can see it. Hold on, let me zoom out a little bit. So what you actually start seeing near seek, which makes sense, right, is you start seeing file names, directories, reading directories, syncing, you see file maps, You see actually printing nearby. You see search here, very relatively nearby. Reading. So this is essentially a representation of embeddings of something that's learned. Why is this useful for us, right? When we're dealing with petabytes of data, we don't want to deal with petabytes of data. There's no dealing, particularly with neural networks, you don't want petabytes of data. More data, we all say, yes, more data is better, more data is great. But when you're dealing with the kind of networks we deal with, particularly LSTMs, recurrent neural networks, that we want to learn and remember something, having more than even a few gigabytes of data in many cases will blow up what the use case is that we want. It will not actually make it better or more effective. This has to do with the limitations of the architectures, with the sizes, in some cases with hardware. So what you want is you want to be able to take that large data set and create small artificial data sets that are representative of what you're looking for. I want to train a neural network to be able to understand security vulnerabilities. I want to start taking the vectors related to known security vulnerabilities, and I want to then start maybe taking all of the functions that are semantically similar or co-occurring in that space and build a data set specific to that. And I just made this one up on the spot. But at the end of the day, you want to be able to use whatever you have early on to narrow down your data or to filter it at some moment. So just for the sake of time, I won't go too much into, where was I? Into tree-based LSTMs. This is just what I showed you. So that's a little bit my talk today. I want to thank you guys very much. I hope it wasn't too specific on code, but I also hope to show you just a few general trends, right? Consider doing things on GPUs, look at your infrastructure, not just how everyone else is doing. Don't go straight to the cloud. Make sure you make a conscious decision for doing so. If something seems really, really hard or expensive or impossible, in most cases it can be solved. And don't always think that more data is better, because it really in many cases isn't. And in many cases also you don't need labeled data. Almost everything I showed you today did not use labeled data. So yes, it is more hard. It's always better to have labeled data. But if you don't necessarily think that machine learning can apply to you. So thank you very much.
Your team, and
yeah.
You mentioned that you have a lot of people in Russia, a lot of people maybe in Europe, Southern Europe, different locations. Yeah. One of the principles people have been thinking about building team is you get different experience, different location. I mean, like even in the Bay Area, you have people that are, yeah. And I'm not saying you need.
No, but I know exactly what you mean.
But it's an experience.
Yeah, so location linked to experience, essentially, right? So I must correct, so our team is fully based in Madrid right now. We are now just starting since the last few months allowing people to be fully remote. That has more to do with the culture of our company. So we actually, everything about our company is transparent. You can go on our GitHub and find out how much stock I own or what our holiday policy is or how much options people get. Pretty much everything that we do is out there. In terms of location and experience, so I can personally comment on the fact that I've lived out here. I've got to live in Asia for some time, and I've got to live, originally from the Netherlands, and I've got to spend some time in different hubs in Europe. I'm still young, so my opinion is not remotely as valid as somebody who has more experience in this field. But what I've seen is the following, is that in many cases today, at least in the field of machine learning, or let's call it AI or deep learning, there's definitely certain hubs. So you have Montreal, you have San Francisco, you have Paris being one of the main hubs in my opinion. And those are essentially the academic hubs, right? The hubs formed around certain form of academia or SF, the Bay Area in this case, around industry. What I've seen in the field of deep learning is that it's pretty much not location dependent in terms of finding experience, as long as the people in this field are out there reading the latest papers, going to the conferences, making connections. Right? Some of the guys on our team, we have this concept called Open Source Friday, which means every second Friday the whole company only focuses on working on something that's open source, and it's the only rule. It doesn't have to do anything with the company, it can be about anything you want. And I have some of the guys on our team who are working with guys in LA or in San Francisco or contributing back to Comma AI, right? So what I've seen is that this has become relatively democratized. Another thing that I've heard quite often from CEOs out here, particularly European CEOs out here, is that they don't want their hardcore deep learning research to be here in the Bay Area. for two reasons. One is the talent pool is not that large, and it's highly concentrated at companies and places that can pay a lot, Facebook, Google, OpenAI, etc. So in many cases, they end up having their hubs in Paris, sometimes in London is one of the hubs, for exactly that reason. But to be honest, I've seen great talent all over, and I think as long as you're connected to it, it works okay. One of the things that helps offset this, and this is what we actively do, is fly people around for conferences. Right? So I have our team here, different people coming here all the time. We are pretty much all over the world to be able to get some of those insights or those relationships that you can't get unless you're here in person. But it doesn't feel, at least for this field, in other fields I do so, that it really matters that much. Yeah.
This is an infrastructure question.
Yeah.
How do you deal with the network bandwidth?
Yeah, so right now we've, you mean a network bandwidth problem inside a cluster or between clusters?
Or between clusters?
So between clusters, there's not much you can deal with besides making sure you get the fastest possible line from your local provider. It's literally as simple as, in our case, of literally calling the local provider and say, look, we want a direct link, 1 gigabyte a second link. That makes a big difference. In terms of inside the cluster, we heavily rely on Matchbox, which is a project by CoreOS for the networking. We've been contributing to it. In most cases, one of the things that you can do, what I mentioned earlier, is if networking is an issue inside your cluster, is to move containers instead of moving data. This helps. And trying to process as much locally. So one of the things that we optimize Spark for internally is to, and it does it by nature, but we try to go quite far, is to move as little data around as possible.
Business question, why would I pay you and for what?
Yeah, so very good question. So yeah, it's probably like half the question's answer. I should have mentioned this up front. We're a little crazy. What we believe that code will become as big of a field as natural language or computer vision. And when it does, we want to be the company that has built the entire stack below it and can come into Google or into Facebook or IBM and say, look, let us train custom models on top of your code bases. Right? Let us take the entire tooling, infrastructure, everything that's out there, and let's be the one that do it. So it really is a big bet on this becoming a field. I will say we're very privileged and lucky the fact that we have the funding and the investors who are willing to invest till that actually happens. The analogy we often draw is to the field of containerization. Right? Docker went, a small company out of Paris, moved out here, created the field of containerization essentially. And now there's an entire industry with an ecosystem that makes it a viable commercial entity. Today it's not yet. But to give you an example, when you have things like automated testing or vulnerability detection, all of these things require custom models on top of private code bases. And to be able to really get value from that, you need to train inside. And we feel that right now, and hopefully in the next few years, we're best positioned to be able to make that happen.